Things. This is crunch. This is supposed to be dead week, isn't it? Students hate it. Whenever. What's that?
Instead of the campus dying, the students just slowly die.
It's dead week because there's so much to do that we're dying.
Oh, that's why they call it. It's not dead week because there's no more assignments.
It should be that way.
It should be that way, but dead, yeah. Well, deadlock during dead week. Yeah. Okay, well, what I would like to do, there's just a few more, we've got two more examples, and then I would like to say something about C++. Now, so let's think about, here's another classic problem. There are several just really classic problems in concurrency. One of them is the bounded buffer, producer-consumer problem with the bounded buffer. That's just a classic. Everybody knows that. I mean, that's just one that, because it's so common. And another one is the dining philosopher's problem, but that's not famous because it's practical. That's famous because it's such a good, like Towers of Hanoi, it's just such a good problem to simulate to see how these parallel algorithms work. And there is a third one that is just a classic, and this one is really important because it's really practical. And this problem, and so you really need to be familiar with this. So what we'll do is we'll take a look at, we will describe the problem, and we'll take a look at some code with a monitor that solves the problem. And I think you'll see how neat monitors are when we work through the problem here. The problem is called the readers and writers problem. Now what we have is readers and writers, that's plural. So what you have is there's a shared database with many readers and writers. Okay, so you have this database, and you want to be able to have a lot of people access this, read from the database at once, concurrently. Do you see what I mean? You want them to be able to, because after all, by reading it, you're not changing anything, yeah? So you imagine this scenario. It's kind of like there's this library book, and all these people, all these readers are getting into this library, and they're all reading this book. They're looking over each other's shoulders, and they're reading all this at the same time. Or maybe they're reading different books in the library at the same time. But then what happens is you have a process, you have another concurrent process that wants to change the content of the database. Change the content of the book. And so you can't have people pulling information out at the same time it's being changed. So you want to have a situation where the writer, there can be many readers at one time, but there can only be one writer at a time. And so a writer has to be able to get into the room and do the mutate the database, change the database. And he has to be able, and when the writing is happening, to keep things consistent, you don't want anybody else reading, because if they're reading at the same time he's writing, they might read something that's in an inconsistent state. So you want to have only one writer have exclusive access to the database when the writer wants to write. And then after he's finished writing, then you can have a whole bunch of readers come in and read at the same time. Do you see what I mean? And furthermore, of course, you also can't have two writers. So anytime you have a writer in the database, that one writer has to have exclusive access. But anytime there's no writers in there and a whole bunch of people want to read at the same time, that's fine. Now, does everybody understand the situation, the scenario? And so you might think that this is some kind of a database that is accessible on on the internet. Maybe it's and these people are all coming and they're accessing this database at once. But then you want to change the database. So now what you have to do in order to change the database, as these people are entering and reading this, you have to get them all cleared out. You see what I mean? You have to get them all cleared out so that the one writer can go in and change it all by himself. And then after that writer leaves, then you can let the floodgates open again. You have a bunch of readers in. So that's the scenario. Now, in order for this scenario to work now, we're going to have to kind of like backtrack a little bit from the whole idea of the monitor, because what we're going to do is we're going to have we're going to have 4 monitor methods, and let's just jump ahead to the this jump ahead to the this slide. Let's jump ahead to the reader and the writer code of this, and we'll skip the monitor here, and let's just take a look at what the reader at what a reader does. So anytime a reader wants to read from the shared database, he executes this. RW stands for readers, writers. That's the name of our monitor. So the reader executes start read. So we have to make sure that the reader code calls start read and calls these in its code, right? So the reader writer the reader executes rw.startRead. Then this reader reads the database, and then after the reader's finished reading the database, he executes rw.endRead. So start read and end read are monitor methods. Okay, and similarly for and there could be a whole bunch of readers who are doing this. And similarly for a writer. Okay, in order for a writer to start, a writer executes rw.startWrite. Now, what is startWrite going to have to do? This writer is going to have to block this writer if there are readers reading. And as those readers get finished reading, as they execute as each one gets through and executes end read, if there are more readers that are trying to get in, we don't want to starve the writer. You know what I mean? So more readers. So as these readers get out of this database and execute rw.endRead, the last reader that ends this needs to signal this writer so that one writer can get in. And while this writer is in there, the readers and other writers can be piling up, executing their start reads and their start writes. They can be piling up, but this writer has to have this one writer has to have exclusive access to write this database. Then after he's finished, he executes rw.endWrite. So does everybody see then that this monitor provides 4 methods, one for the reader to start, and the one for the reader to end, and one for the writer to start, and the one for the writer to end. But that's the scenario. Okay? So now, here's the code, and it's just so neat. Here's the code for the monitor. So let's take a look at this code, and this is in our language independent code that is very similar to C++. So check it out. What attributes does the monitor RW have? It has an integer called readers initialized to 0. So what do you suppose readers stands for? The number of readers that are in the database reading. Yeah. Okay. And also writers gets 0, initialized to 0. So that's obviously the number of writers that are in the room. Now hopefully number of writers can never be what? More than one. Yeah, that's the whole idea. Okay, so hopefully the number of writers can't be more. But the number of readers could be more than one. But not simultaneously, right? You couldn't. You don't want to have writers and readers both greater than 1. Okay. Or both greater than 0. Rather. Okay. So now, first of all, let's take a look. So here's the 4 methods, and I've underlined them here to set them apart. So. Oh, wait, sorry. 2 more variables, condition variables, OK to read and OK to write. Now, by now, do we know what's associated? We just said it a few minutes ago. What's associated with each condition variable? A what? A queue of blocked processes. So there are processes that are blocked on OK to read, and there are processes that are blocked on OK to write. Yeah? And now, let's take a look at from the reader's perspective. So what we have here are Operation start read and operation end read. Okay? And here's operation start read. So how does a reader get in? The reader gets in by doing start read. So what's the first thing that start read does? It checks if what? If writers is not equal to 0. Now, if writers is not equal to 0, is there a problem or no?
Yes.
There is a problem. Right? So if writers is not equal to 0, there's a problem. And how about this? What else does it check? What is this? Empty, okay to write. But now wait a minute. What is okay to write? What is this? That's the queue of block. Yeah, that's the queue. So it's checking to see if that queue is empty. So it's checking to see if the queue, okay to write, is empty or not. Okay. Now, now when's the problem? What did we say the problem was here? The problem is if the number of writers is not equal to 0. And what's the problem here? Why would this be a problem? Not empty, okay to write.
Because if it's not empty, that means that there are other blocks.
There are some block processes that are blocked on okay to write. So how could that happen? Who gets blocked on okay to write? Some writer. So do you see that this means, what does this mean? What this means is, you see a reader is trying to get in, but when he checks empty okay to write, he's checking to see, wait a minute, some writer has blocked and is trying to get in. And who has to get in first? If there's a writer who's blocked, trying to get in to write, and this reader's coming in, but say he's blocked, there's a writer who is blocked, and that writer is trying to get in. So what does the code have to do? It has to prevent the reader from getting in and starving him. You see what I mean? Does everybody see how that works? We'll do a little trace. We'll do a little scenario here. Okay. So in a minute. Okay. So in that case, what do? Wait, see, okay to read. So what is it? So in under those two problem circumstances, what does the reader do? Puts himself onto the what? Queue of block processes. Are you with me? And here again, the wait see is in the body of an if. That's the idiom for programming with monitors. And then eventually, we presume, if the code is written correctly, eventually this reader is going to get signaled. Are you with me? And once it gets signaled, it'll come out of the queue. And then what will this do? Readers gets what? Readers plus 1. So we add 1 to the reader count. Yeah. And then we signal, and then we signal see okay to read. Okay? So when we signal see okay to read, what does that do? If somebody is waiting to read, we signal that.
And is that because once that wait C is finished executing, that means someone is reading? But since you can have an unlimited number of readers, you can unblock
yes.
other ones.
You can, yes. Yeah. Okay. And now, so then after the reader reads, after the reader executes start read, and now that reader is reading, and now what happens when a reader is finished reading? He executes end read. And so operation end read does what? Readers gets readers minus 1. And then if readers, now, once readers gets readers minus 1, then there's one fewer reader, right? But we have to take into account the fact that a writer might be wanting to get in. So if readers equals 0, after we subtract 1, we signal C okay to write, because this means if readers equals 0, that's the last reader to leave. And if that's the last reader to read, we better do a signal C okay to write in case there's a writer who is blocked on getting in. And now let's take a look at Operation start write and operation end write. And then we'll go through a little scenario. If writers, so now here's a writer. The writer's trying to get in, okay? And what's he? And so what happens? When is it a problem? If another writer is already in there, okay, that's a problem. Yeah, because there can only be one writer in there at a time. So if writers is not equal to 0, that's a problem. Or what? Readers. So if there's any readers or writers in there at all, what do we have to do? We have to wait C, OK to write. Yeah? Okay. And then after we get unblocked, then we do writers gets writers plus 1. That's it. And then operation end write. Well, now end write, we're about to leave, so we do writers gets writers minus 1. And now we check what? If what? Empty, OK to read. So what does that mean? No, there's no readers that are being blocked. Then what do we do?
So it's okay to write.
We signal there might be a writer who wants to get in. Yeah? Otherwise, we signal OK to read. Okay? So one of these two is going to execute, and one of those two, whichever one executes, that will be the last statement of the operation.
What if both okay to write and okay to read are empty?
Then it will signal, this is an else. It will signal, if OK to write is empty, no wait, if OK to read is not empty, it will signal OK to read. Wait, did I say that right?
What if okay to read is empty and okay to write is empty? What does it say?
It only checks OK to read.
So can it signal something that's empty? Like,
Yes, yes, it can. In which case it just goes on. All right, now to see how this little scenario works, let's do this. I have a sequence of events, and let's trace through this. Okay, to understand how this sequence works, we need to understand 3 points about this solution to the readers and writers problem. The first point here is that new writers are blocked if any readers are active or if a writer is active. So let's look at the code to make sure that's the case. So new writers are blocked. So here's the code for start write. It says if writers is not equal to 0, so that means if any writers are active, or readers is not equal to 0, so if there are any readers are active, then we wait C in the body of an if. We wait C OK to write. So that establishes that first fact, that new writers are blocked if any readers are active or if a writer is active. Now the second point is that an existing writer unblocks any blocked reader rather than a blocked writer, and consequently all blocked readers enter. So this is kind of like a cascading effect. If there's a number of readers that are blocked and a writer exits, what happens is that all the readers that are blocked, they all come into the database. So let's see if the code reflects that. We say an existing writer unblocks any blocked reader. So we need to look at what happens when a writer ends write. So here we have operation end write. So there's a writer, and the number of writers gets writers minus 1. So actually the number of writers can only be 0 or 1 in any scenario. And so if the writer executes operation end write, after the number of writers is decremented by 1, it says if empty, OK to read. So now let's assume that there are a bunch of readers blocked. So empty, OK to read is going to be false, and the else will execute, and the writer will execute signal C, OK to read. But now look, when signal C, OK to read executes, then let's see what happens to the readers. So the readers will be blocked. Here, let's look at this code. And so the let's assume that that a number of readers are blocked so that they are in wait C OK to read. So in operation start read, after wait C OK to read, the first reader will be unblocked. That reader will execute readers gets readers plus 1, incrementing the number of readers by 1. And then that reader will signal OK to read again. And by the immediate resumption requirement, that the second reader will execute readers gets readers plus 1 and again signal C OK to read. And then the third reader will immediately resume, execute readers gets readers plus 1 and then execute signal C OK to read. And that cascading effect will let in all the blocked readers who will be able to be in the database reading at the same time. So that code establishes this second point. An exiting writer unblocks any blocked reader rather than a blocked writer, and consequently all blocked readers enter. That's kind of like a cascading effect that we will illustrate in a minute here with this scenario. Now the third point is that any subsequent incoming readers will be blocked by the blocked writer, who will eventually enter when the last active reader exits. So let's see what happens if a subsequent incoming reader tries to enter when there is a blocked writer. So here let's go to the code for start read. So if a reader comes in, if writers is not equal to 0, so if there is an active writer, or a writer is blocked or not empty, OK to write. So or if a writer is blocked, then the reader is blocked because it executes wait C OK to read. And then the writer will eventually enter when the last active reader exits. So now why will the blocked writer eventually enter when the last active reader exits? So let's see what happens when we do end read. Okay, so here's the code for end read, and we see that if the last reader exits, it tests if readers equal 0, signal C OK to write. Okay, so that establishes the third fact, the third point. Now, here is the scenario that we will trace through to illustrate these points. What we have here is, first of all, for sure we're using Hoare semantics because this is our binary monitor, in which case E is less than S is less than W. So we don't need the wait queue because we of the immediate resumption requirement, because the signaled, it resumes immediately, and the signaler might be put in the S queue. And so we have a stream of readers and writers trying to get in. We have 3 readers first, followed by a writer, then a couple of readers, a couple of writers, and a bunch more readers. So let's work through this scenario and see what happens. Okay, so the first thing is we do start read. And 3 readers enter because writers equals 0 and OK to write is empty. So now let's double check that code. So when we do start read, you see writers is 0, or not empty, OK to write. So both of those are false because there's no writers. And so readers gets readers plus 1, and we signal C OK to read. All right, and so 3 readers can enter because writers equals 0 and OK to write is empty. So there's the 3 readers in the database reading more than 1 reader in the database. The next thing that happens is the writer tries to get in, but what happens is the writer is blocked on OK to write because readers equals 3. And so to double check the code for this, on the start write, if writers is not equal to 0, okay, but that's false. But if readers is not equal to 0, but that's true because readers is 3. So therefore, start write executes wait C, OK to write, and the writer is blocked. And so there he is in the OK to write queue on that condition, on the condition variable OK to write. Now the next thing to happen is you see a reader is trying to get in. So what happens there? Well, when we do start read, the reader is blocked on OK to read. And here again, because OK to write is not empty. So we can double check the code for that real quick. And you see when we do start read, it says if writers is not equal to 0 or not empty, okay to write. And not empty, okay to write is true because there was a writer blocked. So start read executes wait C, okay to read, and that reader is blocked. Because okay to write is not empty. Next we have the case where the readers, one of the readers exits. So when that reader executes end read, the first reader exit does not signal, the second reader to exit does not signal, and the third reader to exit signals. So this is that cascading effect that we were talking about before, where you see on end read, if readers, the first reader that exited, if readers equal 0, did not signal okay to write. And the second one, if readers equal 0, did not signal okay to write. But the third one, after decrementing readers against readers minus 1, readers was equal to 0, so the third one did signal C okay to write. So therefore, what that did is that unblocked the writer. And so in this code, we see that when the writer is unblocked, the writer had executed start write, and so he executes writers, gets writers plus 1 in this code, and therefore the writer now is in the database, the sole writer who is writing in the database. So the writer is unblocked and writers equals 1. And now what's going to happen is we have another reader trying to get in, and so that reader gets in and does start read, but of course because there is a writer, that reader is blocked, and so here's the picture. The next reader to enter is blocked on OK to read because writers equals 1. And then we have another writer trying to get in. So he executes start write, but then he is blocked on OK to write because writers equals 1. So now let's suppose that the writer in the database eventually finishes writing the database and exits. So what happens when he exits? He executes end write, which then he decreases writers, gets writers minus 1, which makes writers equal 0. And then the exiting writer signals OK to read because OK to read is not empty. Now, the exiting writer may be blocked on S, but this is inconsequential because signal C is the last statement of the operation. It will immediately exit because E is less than S. So to see that code here, when the writer executes end write, it says if empty, OK to read, but OK to read is not empty, so therefore he signals the OK to read, and then goes to the S queue. But because signal C is the last statement of the operation, he immediately exits, and so consequently the first signaled reader resumes and sets readers equal to 1. And it signals the next reader, so we have this cascading effect so that the readers all enter the database, with the writer being blocked on OK to write. Now what happens is we have a situation that we had similarly before, where any readers and writers entering the monitor are blocked on either the writer is blocked on OK to write, the readers are blocked on OK to read. Eventually the readers will exit, and the next writer in the OK to write queue will have exclusive access to the database. So that's a summary then. I think we've covered all the scenarios. That's a summary of how the readers and writers problem is solved with this algorithm using Hoare semantics. Okay, so now that we've seen how to solve the readers and writers problem with the algorithm from Benar using Hoare semantics, the next question is, how do we do it in C++? Because as we've seen, the C++ uses Mesa semantics. And so actually that algorithm that we just looked at does not work with Mesa semantics. In fact, it will deadlock with Mesa semantics. So the question then is, how does how do we implement the readers and writers problem in C++? And the answer is, with C++ 17, they have introduced this concept of a shared mutex type and a shared lock type, which is designed expressly for the solution to the readers and writers problem. And so here's the concept. There's a shared mutex and a shared lock, and there are two levels of access. These two levels are called shared, which are for the readers, and exclusive, which is for the writer. So with the shared level of access, several threads can share ownership of the same mutex, whereas with exclusive access, only one thread can own the mutex. And the way it works is that if one thread has acquired the exclusive lock, no other threads can acquire the lock, neither the readers nor the writers. And the shared lock can be acquired by multiple threads, which are readers, only when the exclusive lock has not been acquired by any thread, which is a writer. So here's how it works. We have a we'll see. We will look now at the code of a project in our distribution software called Readers Writers A, the Readers Writers A project. And what it illustrates is this is the way to solve the Readers Writers problem in C++. Now what they did in C++ is they built in a different algorithm from the one we just looked at, and this algorithm is called the Terekhov algorithm. And it's for shared and exclusive use of the shared mutex as a solution for the readers and writers problems. So basically what they did is, in C++, they basically solved, they give us a solution to the readers writers problem with these with this shared mutex concept. So here's the code now then looks extremely simple because of this feature that is built into with these C++ features of the shared mutex. So here, let's do a little code walkthrough. So now our monitor is called RW database, and we have, well, the way we're going to illustrate this is we have a private int named myData, which is initialized to 5, and what the readers are going to come in and read myData and stream it out, report it out. And the writer, what the writer is going to do is it's going to increment this 5 by 5 each time. So make it 5, and then the next writer will make it 10, and then 15, and so on. So that's going to be our little example of a database, the shared database. And here we have our RW mutex, which stands for reader-writer mutex, now is a shared mutex. And then we have our usual, we have a little auxiliary cout mutex named mutex, just so that our cout methods will not be interleaved. And so the monitor provides a read my data and a write my data. So it's all very simple. And read my data, so let's do a little code walkthrough of read my data. So the first line of read my data has a shared lock, which takes as a template parameter a shared mutex, and then we have our usual guard, which gives it the which links the RW mutex to the shared mutex. So because this is a shared mutex, that means that several readers can read it at the same time. And then here we have a little cout mutex. Because we can have several readers reading at the same time, we need a little cout mutex to make sure our cout line does not get interleaved. And so we have a little binary mutex surrounding our cout, which just says reader and then gives the reader ID, is about to read. And then we have a little random delay of 60, and then we have a cout mutex lock, and we output reader read, and then the reader reports the data that he read. And then, of course, by that RAII feature, the shared mutex is unlocked when the last reader exits my data. And then for the write my data, which takes a writer ID as a parameter, we have the lock guard, but this time instead of having it be a shared lock, it is a lock guard, which means that the writer has exclusive access to this method. And then we have an output statement that says writer is about to write, and then we have a little random delay, and then the writer increases my data by 5 each time.
and then we see out writer wrote, and we report what the writer wrote. So there it is. It's a very simple, because C++ built in this solution to the readers-writers problem with this shared mutex concept. The code is quite simple, at least on the surface. But behind the scenes, it's another story. All right, so here is here we declare our RW database, which is just an instance of the capital R, capital W database. And then here's the code that the readers execute. So it's called reader run, and it takes a reader ID, and we're going to have it loop 3 times for I gets 0, I less than 3, I plus plus, and the readers will just execute RW database.read my data, and pass the reader ID. So the readers will read the data, and then similarly for the writer run, it will also execute 3 times with a little random delay of 60, and then it will just call write my data. And then here's the main program. So in the main program, we just start up 3 readers, and we start up 2 writers. We give the readers IDs of 0, 1, and 2. We give the writers IDs of 0 and 1. And then we just join them all, and that's it. Okay, so now let's do a little demo. Okay, so here's our demo. We have our CLion IDE here. And here's the code that we just did a code walkthrough on the slides. Here's our RW database and our little local int my data, which is going to get incremented by 5, and here's our shared mutex, RW mutex, and then here's the read my data method and the write my data method of the monitor. And notice that they are using the shared mutex for the with the shared lock for the read my data, whereas we're using the shared mutex with the lock guard for exclusive access to the write my data. And here's the reader run and the writer run. And here's our database. It's just a little global instance of the monitor named RW database. And then here's our initialization of the 3 readers and the 2 writers. Okay, so let's give it a run and see what happens. Okay, so let's examine the run here. So let's take a look at what happened here. So reader 0 is about to read, and then reader 2 is about to read. So they're both going to get in there at the same time, it looks like. And sure enough, reader 2 reads 5 and reader 0 reads 5. And then the writer was trying to get in, and after those 2 readers left, they probably cascaded out of there. And the writer got in, and the writer increased it 5 by 5 more and made it 10. Oh, and now another writer is trying to get in. Writer number 1 is getting in, and he has exclusive access and is increasing it to 15. Then reader 1 and 2 and 0, so it looks like they're all getting in there at the same time. And they each are reading to 15 here. And then the writer got in and increased it to 20. Oh, and then another writer increased it to 25, and then the 3 of them got in again. And they read to 25. Once reader number 2, look, 0 is about to read, 2 is about to read, 1 is about to read, but then 2 read, and then 0 read, and then 1 read. And then writer 1 is about to write, he got it up to 30. And the writer 0 got it up to 35, and then reader 1 took the last read and output to 35. Let's try it again and see what happens. I'm sure it'll be different, but it should all work. Okay, so here, they all 3 got in at the same time this time, at the beginning. And so all 3 of them read 5, reader 0, 1, and 1, 0, and 2. And then writer increased it to 30. Another writer increased it to, wait a minute, what happened here? Oh no, the writer 1 increased it to 10, and then the writer 0 increased it to 15, and then the 3 of them got in again. So sometimes the 3 of them get in all at once and get to read. Looks here like a couple of them got in this time. And so each time we do this, it's going to be different. because of the random delays, but in any case, it all appears to be working correctly. Let's do it one more time. And sure enough, see here it's different. Instead of all three of them getting in here at the beginning, number 2 just got in, and reader number 2 just got in and read the 5, and then writer 0 increased it to 10, and now all three of them ganged up and got in there at once and read the 10, and so on. So that's a nice little demo of how the readers-writers problem works when it's executed using the C++ built-in Terekhov algorithm to solve the readers and writers problem. Okay, end of demo. Okay, so that concludes our demo, and it's rather, it looks rather simple, that the solution that the shared mutex gives us to the readers and writers problem, but what's going on behind the scenes is quite interesting. And so what we're going to do next time is we'll have a screencast of some additional details about how that Terekhov algorithm works. And so we will be looking at 3 more projects that are in the software distribution for this course. The next project that we will look at is the Readers Writers B, which is an implementation of the Terekhov algorithm without the shared mutex. And so this, we will actually be able to see the algorithm that the C++ designers provide with the shared mutex to see the logic of it and how it works. And then also we will take a look at the project Readers Writer C, which is the optimized version, an optimized version of the Terekhov algorithm. And this is the actual, we will actually be able to see exactly how the designers implement the shared mutex by looking at this optimized version. This is taken from their reference reference implementation. And I have a little, so we'll be able to see these interesting optimization techniques. It's beyond the scope of this course really to look at this level of detail, but if you're interested, we will do that. And then also, as a little final demonstration, we will take a look at the Readers Writers D project. And what I've done here is I have actually implemented algorithm 7.4, the one that we just looked at, using that is correct for Hoare semantics. And we will see that if you implement that algorithm with Mesa semantics, the algorithm actually deadlocks, and so it doesn't. You see, there's a crucial difference between the behavior of a Hoare semantics. An algorithm that works with Hoare semantics might not work with Mesa semantics, and vice versa. So that we will demonstrate that in our screencast in our next video once that gets published. All right, so that concludes the topics for the Programming Paradigms course. Thanks for watching, and see you later.